Now we are going to ask ourselves the question of how to interpret a network analysis result. The language of graph theory is not that of the historical sciences, which is why I propose to speak of a translation practice. How do we appropriate the toolbox provided to us in order to derive valid results for the humanities? How do we translate the metrics into our language, for example? We distinguished three levels of analysis that can be articulated: the visual analysis, top left here, that consists at looking at the overall organization; the global metrics, bottom right, that measure general characteristics of the network; and the local metrics, bottom left, that describe the position of one element among the others. Regarding visual analysis, the way we read network has changed over time. Historically, the question of network readability was asked in terms of aesthetic criteria. For example, Moreno, we saw in a previous chapter, explicitly sought to avoid edge crossings. When giving birth to the modern layout algorithm, Früchtermann and Reingold, 1991, aimed at minimizing edge crossing and reflecting inherent symmetry. We call diagrammatic the perspective where the network is a diagram that we read by following path. We do not want the edges to cross, and we use aesthetic criteria to bring clarity. It is still relevant to small networks and local exploration. Then we call topological the perspective where the network is a structure that we read by detecting patterns. We expect the visualization to help us retrieve structural features like clustering or centralities. It is a common practice in digital history, more holistic and relevant to larger networks. To illustrate our very heterogeneous relationship to visual network analysis, here are some examples from the abstracts of recent DH conferences. Networks appear to have a wide range of usage. The visualizations are either self-sufficient, an optional help to understanding, or strongly connected to the text. Some authors use them to highlight the position of a specific node, or it can be used to compare layouts to or the layout of the same graph in time. They may aim at visualizing communities, or they can be used at mapping a general structure, sometimes considered a map, or tracking density patterns, monitoring algorithms like modularity clustering. Regarding the metrics, we've already seen that they are often opposed to visual interpretation, of which they are supposed to be a more objective and reliable representation. But graph metrics have a history that goes back to more than half a century, and it shows that they are not immutable and require constant adaptation to usage. Moreover, Lyndon Freeman in 1979 insists on the fact that the notion of centrality is the result of several intuitive conceptions. To remind that these metrics are based on intuitions means to recognize that they have no meaning in themselves, and that their interpretation must be rediscussed and therefore translated according to the context. In the following slides, I will therefore list the most commonly used metrics and suggest ways of translating them to show where and how they are generally interpreted and in the historical sciences and the humanities in general. Statistical analysis allows for comparing networks across multiple dimensions at once. For instance, comparing the number of nodes and edges of different graphs of the same type can be a ranking tool that is directly translatable into natural language. The relationship between these two very simple measures, the density, is a very good indicator when comparing large networks, in which it is not possible to count all the elements visually. The diameter can be used to describe how the density is distributed. Complex networks are often characterized by a small diameter, while high diameter is frequent in geographical networks. It can be translated as the width of the network. The average path length could serve as a complement to diameter, because the latter can be influenced by a few nodes that are very far from the main component of the graph. Like the previous one, it can be used to describe the size, breadth, or width of the network, but it can also be translated into an indicator of a small world situation. Connectedness is quite a simple global property, and I already mentioned the importance of distinguishing networks where all components are connected from disconnected networks. On the contrary, clusters or community detection are widely used. It is especially useful for exploration, but be careful, it is tempting to take the result of a cluster calculation as given. In some cases, it is interesting to compare these clusters with previously known groups, categories that do not depend on the structure obtained. In terms of translation, this notion of community is very directly related to the way in which the social sciences and humanities use the metaphor of the network. The global or average clustering coefficients are complementary to the community detection. They give an idea of the entanglement, intrication, and the presence of a more localized density. With regard to local measures, the degree, number of neighboring nodes, is the simplest centrality and the only one systematically used between the late 1950s and early 1970s, before the development of more diversified metrics. Its simplicity allows for a transparent translation. In a literary network, for example, it counts the number of times one character speaks to another. The notion of betweenness centrality disrupts the conception of what the center of a network may consist of. Its ability to reveal structural elements bridging large, immediately visible clusters makes it popular in the social sciences since the emergence of Granovetter's concept of weak ties. Betweenness is very closely linked to the notion of circulation. It counts the shortest path to detect intermediate bridges or key passages capable of opening or locking certain parts of the network. Depending on applications, these are therefore both position of power and vulnerable places. The closeness centrality allows to highlight the geographical middle of the graph. In networks of a certain density and when they are not divided into several distinct communities, the closeness is generally fairly evenly distributed and allows a good translation of the notions of center and periphery. For its part, the eigenvector centrality is quite complicated to translate since it works iteratively and is very much dependent on the structural contexts at short and medium range around the node. It was named power centrality by its author. It's an indicator of prestige or influence. It qualifies a node's environment while operating in cascade. A well-connected node gives its neighbors a part of its authority capital, and so on. It is therefore particularly useful when trying to analyze the hierarchy of the nodes in a graph. The local clustering coefficient is also a metric making possible to analyze relationships at the collective level. It can be translated as an indicator of participation in a group or, on the opposite, loneliness, solitude. In this chapter, I have only mentioned a few possible interpretations, a few ways of translating these measures and observations into the language of historical analysis. But each of these approaches could be discussed in detail, whether it be visual analysis or metrics. Of course, the analysis should not be limited to a catalogue of well-known methods, basic centralities, etc. In fact, approaches combining several of those should be encouraged to obtain an optimal and innovative translation. In this way, we could compare metrics or combine them to establish rankings. Furthermore, the enrichment of the networks by means of categories that are not dependent on the structure, like the gender of individuals in a social network or the disciplines of project in a scientometric analysis, allows to test the translation and interpretation hypothesis by avoiding the blind approach of testing all possible graph metrics.